Hello to everyone. Welcome to this new video on my channel in YouTube. My name is Mariotti, and if you don't know me, I'm the owner of this channel. I have published it on my YouTube channel a series of lectures about sensor fusion and artificial intelligence. And on this new series of videos, I would like to go more in deep in some specific topic related to artificial intelligence and machine learning, which is actually my domain of expertise. Although, given the complexity of these topics, I realize that actually my knowledge is definitely not enough to cover in deep and with a really rigorous and technical perspective these specific topics. So today we would like to discuss about what I think is a really hot topic of the current research in artificial intelligence, which is explainable artificial intelligence. So as a machine learning engineer that works in the industry, I've always found sometimes working with neural network and actually what we call black box model, I always found a bit some difficulties in basically explaining why my models are working. So hopefully, I don't know if the answer to this question could be answered at the end of this lecture. Probably not. I think it's a quite ambitious target, but at least I would like to go more in deep in this fascinating world of explainable AI. And to do this, I've asked to my dear friend and ex-colleague Ettore Mariotti to take a lecture about this topic. It will be a lecture-interview. I will try to ask him some questions. Just to give you an idea, this video is targeted for a tech audience which has a basic understanding of the mathematical tools behind artificial intelligence and machine learning, but is not specifically for people in the AI field. So I really suggest to watch this video if you are interested, and even if you are not an expert. So, Ettore, thank you very much to be here, to have accepted my invitation.
Thank you, Chip, for inviting me.
So, just a brief presentation about Ettore. Ettore is a PhD working at CTUS. Have I pronounced it correctly, Ettore?
CTUS,
okay.
Yes, CTUS.
Is located in the wonderful place in Spain, which is Santiago de Compostela. I hope that it's sunny today in Santiago.
Yes, today is sunny. We had 3 weeks of rain, but now today is sunny, so everybody's happy here.
I would say definitely the weather is better than here in Cambridge. Actually, Cambridge is not the worst place in the UK in terms of weather. Actually, the weather here is literally, talking about statistics, I would say that is literally in an outlier considering the UK standards. So we have quite a lot of days of sun, but not today actually. But yeah, at least I'm happy that the weather is a bit better in Spain. So as I said, Ettore is working in his PhD on black box model in explainable artificial intelligence. His research covers topics such as black box interpretability and explainability, machine learning, deep learning, and natural language generation. So, as I said, today I asked him to give us this lecture about explainable artificial intelligence. And so I will let Ettore to talk, because I think I've talked even too much now. So please, Ettore, feel free to start with your presentation when you are ready.
Okay, thank you, Chip, for the kind words, and I think we shall just start and dive into it without further ado. So,
can you share the screen?
Just share my screen,
nice. Perfect.
And yes, I'll play the presentation. If you stop seeing the screen, Chip, just tell me.
Yeah.
So, I like to open this presentation with a question. Did you ever trust? The suggestion is that if you think about it, yes, indeed, you did trust often some algorithms. Whenever you do a search, there are ranking algorithms that are obscure. Like, we know how to design them, but then it's difficult to explain the result. For exploring new songs on Spotify, also even more in a way that is more banal when you drive with Google Maps or when you get recommendation more in general from Netflix. So yes, algorithms and black boxes, but more in general, the algorithm is between us already. No, there are some automated decision processes that are happening even now as we speak. And so, yes, you did trust an algorithm. But there is another question. Why did you trust it? You trust it because it works, because effectively we find that the results are consistently useful in some way. And since it worked in the past, then they are working also right now. So we have a sense of trust that is established through this, the fact that they worked in the past, basically. But now let me ask you another question. Would you ever trust an algorithm in this case? Like, suppose you get, there is in the future a decision support system for a medical, for a doctor. And basically, this system tells the doctor, look, your patient, which is you, is diagnosed with a very rare disease and whose cure is very expensive. Start this $1 million cure. Would you trust the algorithm? Similar things you can think also in legal case. There are some algorithms that were proposed and some that were used for example, recidivism prediction. Will the person still commit crimes if it is let free of the prison? And also more accessible, when you go for asking a loan from a bank, there is this system of credit scoring, like how is it likely that you're going to be paid back? So there is a lot of data. We could in principle leverage some data, but would you trust an algorithm that decides on you or on a loved person? And this is a different question. Here, the answer is you should trust what you understand, because you cannot, in a sense, well, you can, but it's more difficult to just trust because it has worked in the past. Mm-hmm. You know, when you are on the front line, then you really want to be sure that it works, or at least you want to understand why it does what it does, because it might be completely wrong. There were some scandals lately about some decision support systems, for example, used in the criminal justice in the US, that were found to be biased against some certain populations. So also in this world where bias exists and data have the bias, mm-hmm. Because our world is biased, we want to be able to assess that we want to be able to still leverage the data, but also cure the bias that might exist inside it in order to have these support systems.
Sure.
So the question is, how can we understand AI? I like often to refer to this, to see this image, to this story, which is a very ancient story. The story tells about a village in India, I think, because it's an ancient story from India, but a village of blind people, and an elephant comes for the first time ever in this village. And everybody starts trying to interact with this creature and try to understand what it is. And the only way that they can know what it is just by touching it. And everybody has a different perception of it. So one person that is touching the tusk say, this is very stiff and smooth. While other people touching the belly say, no, this is flat and this has a different kind of texture. And one on the right say, no, it's like a snake. So what's the point? The point is that when you cannot really see something, there are still ways of interacting with it that can tell you some stories about it. But each story might be different. Mm-hmm. Still true. They might look that they are contradicting, but they are just looking at different parts of the same story. And with the same idea, we can think about explaining the AI like touching the elephant, that is the algorithm, in different parts and see how it behaves and try to get an understanding of what it is. So in my field, you talk about a lot explaining a black box, but what is a black box from an operative point of view, so that we have a lexicon that for which we can discuss things. Sure. Instead of calling the algorithm, let's talk about the black box.
Sure.
So the black box is just a very useful concept in engineering, where you have some inputs that are processed by this black box, and you have some outputs. The important thing is that the box is black, meaning that you cannot see inside. And so you can only see input-output relationship. You have things, crunch, crunch, crunch. You don't know how the crunch is done, and you only see the soup at the end, in a sense. And this is the first thing. Another question that might sound trivial, but this is not, is what is an explanation? Because if you dig very deeply, you find out that it's not very straightforward or trivial even to answer to what is a question. I will propose something that we are people that have different representation of how the world works. Sure. And of relationships of facts. And an explanation, from my point of view, is a transmission of a fact through, in this case, language, in our human case. And also take care, we need language, but also we need a representation of the world that is roughly similar to each other in order for me to explain to you a fact. And this is already, we can see that there is the beginning of some intricacies when we try to make an explanation from a decision system, because the decision system, the algorithm, may be a decision tree, a neural network, a linear model, a support vector machine, Bayesian network. They might have in principles different representation of the data of the world. And the question becomes, what fact do you want to know? What fact is even interesting to you, and how to communicate it? So it's very faceted. It's like an onion, if you want.
Yeah, it's a really big. This is a really complicated question, I would say. No.
Yes, from the outside, it might seem trivial in a sense if you first think about it, but then no, if you dig inside, there are very nuances. Not to mention that an explanation also, it's like a person, for each person, you have in principle a different way that he would like to receive the information. So it's very user dependent, sure. Based on lexicon, based also on requirement or interest of the user. I might say a fact in a very precise way that the user don't care, for which the user don't care at all, is sure. Not very interested in that. So there is also that dimension.
Yeah. I really like when you say that before, and probably this is something that you cover in the next slide, but when you say that we need a language, the first thought I had about this was we need a shared language, because we can have different languages as well. So I can imagine that if I don't know nothing about German, for example. Fortunately, I know English, so I hope that if I meet a German person, he or she will be able to speak English. But if not, that would be a problem because we don't have a shared language. So yeah,
exactly.
Yeah. Sorry,
but it's even worse than that. It's even worse than that with the case of machine learning, because it's not that it's English or German. Mm-hmm. At least you and a German person still share the fact that you see with your eyes, that you hear sounds, sure. That you have smells, that you have emotions, that you perceive the world in a special, that we are big 1 meter and we are not microscopic, or we are not large as a planet. So you also share some common experience, some way of experiencing the sure. world. In a sense, if we want to think about the algorithms as perceiving the world, they might be perceiving it in a very different and in a quote alien way with respect to us. And the very interesting question is, can we bridge this link? Can we get some insight that is useful and of interest, particular with this case that I suggested you before, where there is a high stake scenario? Can we do that? And this is what we will try to answer sure. today. So there are many ways that you can see explainability. One that I really like is you have to think about explainability is about things that are interpretable, so interpretability. So an explanation must be understandable to a human, must make sense, but also fidelity, this other part, also called faithfulness sometimes in the literature, which means, okay, it must be interpretable, I must understand it, but it also must be faithful to the model, must actually describe what is the model really doing. Because imagine that I tell you an explanation that is very persuasive and very sounding. so it's very interpretable. It's very clear, but it's not really telling you what is going on in the model. In a sense, you could see it as a deception, and it's very important to keep both dimensions. And this will be clearer later in the presentation why I strongly think that this is very important. So let's think more about explainability in general, practically how it is done. So there are two things. One below, you have the famous black box that I said you before. And basically, the only thing that you can see is propose different inputs and then observe the output, how it changes the output. And based on how the output changes, you can try to get some interesting insights into how the black box behaves. On the other hand, you can see on top, you can, in principle, design what are called the white box model, so interpretable by design models. What does it mean, interpretable by design model? It means that this model is structured in such a way for which extracting facts is easier. And we will see both approach today, very briefly, of course, because we don't have much time, but in order to have an idea. Also, just a small mention, in the literature for now, these two ways, in a sense, can also be seen as complementary, but are quite different. You know, there is go interpretable by design, so you can be sure that your explanation is going to be faithful because you are really seeing the model inside. Or you can say, look, interpretable models are not very accurate. The black box sometimes can be more accurate than the white box model. So let's explain only the output. And there you have to be very careful that your explanation is also faithful to the model and that you're not just inventing things or approximating things enough that they are interpretable for a human, but not really faithful anymore.
Sure.
If you want, also I'm a very practical person, so there is, you know, you don't have to always use XAI. So there are different steps. So first step, how important it is explainability for you in your task relative to performance? Because, for example, let's suppose we have a decision system that suggests me new songs in Spotify. How important it is with respect to performance? It is not very important. Why? Because if it is wrong, I can just skip it and nothing bad happen. Sure. Okay. So there is also this concept of how impactful it is a wrong decision about it. On the other hand, if it is very important, yes, very important. We go to the right. The idea is go explainable by design. Take an interpretable model and just use that. For example, credit scoring, which is the problem of trying to understand how likely it is that a client of a bank is going to pay back his loan. It's very important that it's explainable because there might be some, as I said before, some biases below, or there might be that the model captures some nuances in the data that are very weird and we don't like it to be. In Italy, for example, I know that it's very, very much regulated by law. And for example, you can only use linear models with specific constraints on the coefficients that you can use in the case of credit scoring. Another case is that explainability is somewhat important, but not really. So there is another branch. Does the complex model perform better than an interpretable model? And sometimes not. Like sometimes you can have white box model that behave well, like a black box. Sure. So if you have to choose between the two, just go with explainable model. No, why you have the good performance and also the explainability capability. If complex model is still perform better, then you want to ask yourself, okay, we need to explain things because we said at step one that still we believe that explainability is valuable somehow. So is more important fidelity or interpretability, as in the sense that I described before? I think that fidelity is always important, but you can sometimes sacrifice fidelity in order to have a more interpretable answer. And based on this, there are different kind of special tools that you can use to propose an explanation. Just as an example, in what sense you can sacrifice fidelity for interpretability. Let's suppose that you ask me, Chip, that you ask me, how is the world? And I can say you, the world is a sphere.
Sure.
That sentence, it's easy to grasp, even though I'm cheating. It's not really a sphere. There is another way that you can see the world as just being it's not a perfect sphere. It's slightly pulled on equator because it's rotating. You know? It's an ellipsoid, yes. Yeah, geoid, yeah. But that you can go further. You can use the geoid. You know, you can see sure. that actually every mountain is defining. It's not smooth. It's rough. Sure. And then you can go progressively to much more level of details. So there is also this idea of propedeutics, like let me explain you something with let's call it a sweet lie, in the sense that I know I'm approximating the truth, but the important thing is to get you the rough idea that then later, if you need, we can refine.
I think this example is really, really cool, and I mean, really tailored for our case. So, if I understood correctly, the problem of the answering just is a geoid, so which is the most accurate answer. I mean, comes to the risk that the person which I'm answering doesn't know what is a geoid. Is it something like this? The problem?
Precisely. Okay. All that is terribly confused. Absolutely. You know, what does it mean to be a geoid? Or, you know, it has a higher cognitive load, you know? So there is this tension also into trying to provide an answer that not only is true, but it's also interpretable. Okay. Well, basically teaching from day zero of humanity has had this problem, no? Sure. Like, how can I teach something to someone? And it's very interesting now that we are trying to approach, in a sense, teaching, but from the computer science algorithmic perspective, because we have to really settle down to some definition, to some evaluations, and who knows, maybe in the future society and universities and teachers will benefit from research in explainable AI. Or maybe not, it's just a speculation, nobody really knows. But yes, let's go on. This is a bird's-eye view of the XAI field. XAI, explainable AI. I think I said it also before. So basically, this is one that I proposed some time ago, and it's very practical. You just go by questions. You know, what do you want to know? First question. This is very important. Then, how can the AI answer this question? How can the AI communicate the answer? And also, how can we assess the effectiveness? It is a very big and large, how do you say, field of how do you evaluate what is a good explanation? Sure. Because it's very difficult to evaluate the quality of an explanation. And a lot of work is being done into this dimension of measuring faithfulness, of measuring plausibility. You must at some point having experiments with real humans, survey-based or performance on a task to understand how they work and so forth. So this is the broad approach. I wouldn't go too much into the details of this because it's large. I'd rather go on with the presentation, but then if you have questions, we can dive into it. No. Much better.
Absolutely, I think that you can go on. So just a point on this. The difficulty on the evaluation, I think, is particularly interesting. I think, for example, just as a brief example of this, could be, I'm asking to you, for example, a computer vision task, where you have to select where is the cat in the image, is quite really well evaluable, no? Because I can have a ground truth that told me that this is where the cat is.
Yes, but no.
Okay.
Because I will show you later that we think that the cat is there, and maybe also the neural network think that the cat is there, but the concept of cat of a neural network might be different from the concept of cat of a human.
Okay, so I will let you go on. Yeah, I will let you go on, and I will not interrupt you on that. Perfect.
Oh, but later we can discuss it. I have a slide on that, by the way. Perfect. She's very interesting. So, okay, you know, this is the bird's eye view, and now I'm going to tell you very briefly how the field evolved, both in the going interpretable white box, and later I will go also how do you go post hoc on the black box. But basically, in the white box, you have this model that you can see inside, basically, and you can think about extracting some stories and then try to telling these stories somehow to the interested user. Let's have like some example of white box are rule-based systems. So there are systems like if this, then class X, or if this other, then class Y. It's really a list of rules that you can read, and in virtue of being readable in a sense, it's interpretable. Linear models, as you might know, you have coefficients that multiply these features. Decision trees is well, basically a decision tree. It's a block diagram. You have a question, which is this feature larger than something? If yes, go to this branch. If not, go to this other branch. And at each node, you're answering a question, and at the end, you have like a probability that this instances of one class or another. And the nice thing about these models is that each part of it, they are composable technically. So each part of their thinking, in a sense, can be can be seen as interpretable, can be seen as understood, and in principle, you can extract some stories from there. We have also to take into account that if the model is too big, then okay, the parts might be interpretable, but the behavior as a whole becomes less and less interpretable. Because, for example, Chip, imagine that you have a linear model, no? So you just a coefficient that multiply things, but you have 20,000 variables, then it becomes very difficult to narrate a story of why this prediction was like this. It's not impossible, but even if you have an interpretable models, if you go very, very, very large, since we human, you know, there is the famous number, we can think about 7 things at the same time, not more than that. Some people 9, but not more than 10. If you have 20,000, how do? You must, as I said you before, tell the story first that the Earth is a sphere, and then the Earth is a geoid later. Maybe you have to tell that the Earth is flat even before going to more sophisticated.
A cycle. Let's start with a cycle.
yes. Let's leave this talk aside. So there is one class of models that I still believe it's interpretable in the structure, and which I did a bit of work, and it's called this generalized additive model. So while a linear model, you just multiply the values x1, x2 by a static coefficient, here you have a more general function that is applied to each feature. But the important thing is that each feature is then, processed independently of all the others. What does it mean? This means that this form is more expressive than a linear model, but still I can just look at one thing at a time to have an idea of how a certain feature affects my target variable of interest, okay? Sure. Be it a probability or a regression. So there is a simple example that, to be fair, I steal from a website. There is this data set that is assessing the abilities of 15 years olds young persons to read mathematics, science, knowledge, blah, blah, blah. And they try to collect data about what is the education index of a population and what is the average score of these tests. And the data set is pretty small. You have these indexes, and the task is, can you predict what is the ability, like this average educational level, based on the education index, the health index, the income index? Can you predict that? And the nice thing is that if you do it with a generalized additive model, you can see very clearly saturation effects let me explain you this picture. So let's focus on health, okay? On top right plot. Sure. On the x-axis, you have how much health is the feature, okay? Like how much healthy is a population. Okay. On the y-axis, you have what the model thinks, the blue line. You have what the model thinks it's a contribution to the overall score. So when you have a specific country, you will have a specific point in this health thing that will and a specific partial score that will add to your target. So this model is in a sense explainable because you can see these functions. This is sometimes called the shape functions because they have a certain shape, I guess. And it can be even insightful. You can see some saturation effects. You can see some behavior. Of course, you are limited into by design, not taking into account interactions. So there might be that healthy but low educated is different than healthy and high educated. But still, this propedeutic simplification, sometimes it's enough to achieve both high accuracy and high explainability. And my personal small contribution in this area was to basically build this generalized additive model, this gamma, as neural networks. So you basically build each of these F as a differentiable component. And why? Because then you can train it with gradient descent, which is a powerful optimizer. But even more, you can put some constraints on the form of the model as a whole in order to achieve even more interpretability. For example, you can impose some sparsity regulation. Okay, so you can see, I said regulation, few shapes. You can say that the total sum of the absolute values of the activation of the functions must be minimized. You minimize an L1 score. When you minimize an L1 score, what you usually tend to have sparse solutions that still behave very, very good. So basically, the idea is to add some additional regularization terms of what you think is interpretability in your case, which might be few shapes or a more uniform shape or whatever, to your target loss, and you jointly optimize those losses.
Ettore, just a question on this specific feature. So in this case, the input feature are held, am I right? I mean, the input feature that you have declared is the one that you show in the previous slide, the held...
Yes, exactly. So I don't know if this is your question, but go on. Sorry, go on.
No, I want just to ask, what are the input features, and in this case, what are the F? I think the F is like what you said before is like the coefficient.
Yes.
Sorry.
No, sorry, I have to be clear. So first of all, we are talking about tabular data in this case. Let's get this clear. We're not talking about images. We're not talking about text, time series. We're talking about tabular data, which means a data set that can be described as a table. So you have columns that represent features, and each row is an observation.
Okay, perfect.
And you see, this there are different ways in which you can compute these blue lines. Okay. Sure. Each red dot is a data point.
Exactly.
Okay? But how do you compute the blue line? You can compute it if you set it up as a composition of differentiable components.
Sure.
That you can train by gradient descent.
Perfect.
No, you just type to write it, and then you optimize, please. There are other methods. Some of them are even faster and already converge to good solutions. But the nice thing about structuring the network in this way is that you can initialize it as the fast methods, and then you can explore the trade-offs between being very accurate and being very explainable, whatever explainable might be.
Okay,
because this is something that maybe I should say more clearly. Practically, we see in the field when we try to develop this kind of models, a natural tension between interpretable models and accurate models. So, well-performing models. So sometimes what you see is that a very performing model is inevitably complicated. Doesn't have to be necessarily, we don't have a theorem that states that you must have complicated model for having good performances. And in fact, sometimes you can find remarkably simple equations that describe rather complex phenomena. But when you try to learn it with actual technologies, you often end up with models that you can think about black boxes, they're so complicated that they are difficult to interpret. Sure. So this idea was, can we explore automatically these different trade-offs and so forth? And with benchmark this model with my collaborators on many data sets, with different other kind of model, and it seems that it's competitive in finding a sweet spot between what you can measure as complexity and what you could measure as performance. And also, and this is something more cool than useful, but I still believe it's nice. When you have interpretable models like this, you can have an interpretable training of a neural network. Have you ever seen an interpretable training of a neural network, Chip?
No, this is why I asked you to come to the lecture, to do this lecture today.
So this is okay. This is a very toy example. But you see on the left, we have data points, random data points, not random, data points coming from a simple function, which is this sine, a sinusoid, with some noise. Not much, but there is some noise. And you have the blue line, which is the neural network. Okay.
What the neural network predicts.
Which is this, okay, which is one of these functions, one of these orange box, okay.
So, Ettore, just to be sure, each of these F can be a neural network.
Yes, exactly.
No, just to be 100% sure.
And in fact, how do you structure this box? Can you see my mouse?
Yeah, sure.
So how do we structure this? I structure it as a sum of these sigmoids that look like a step, basically. Sure. And if you sum all these steps, then you can have something that is like a line.
Sure.
And so here you have different steps and different parameters, and this is the final composition. So what you're going to see here, you can see the steps are these purple lines,
sure.
Purple dim lines. And you will see, and the sum of it is this function blue that is going very, very, very large right now. On the right side, you will see the loss that will hopefully decrease. So this is the training with gradient descent. Basically, the model slowly adjusts to what is the form that the data tells it to do. And so also you can see that sometimes you get this plateau and then you go down, but now finally you can have a sense of what is going on. And I really think that this is very pretty, even if it is not nothing else. And then you see this is by the way an artifact of the Adam optimizer, that sometimes when it's stuck, it augments the learning rate and it oscillates a bit to see it was stuck in a local minima. Okay. Another thing that you can do, another idea that exists, is can I have a white box that behave like a black box? And this is an ongoing exploration for me personally, and it's the idea of surrogation. Okay, so we have this black box. We still want to use this black box because it works very well. Can I train a white box, not on the data, but on how the black box predict certain inputs? So on the input-output relationship of the black box. Usually what do you have? You have your tabular data set or images or whatever you have, and then a label. In this case, it's another thing. You have the data set, but instead of having the label from the data set, you have the label that the black box think. And if you can build a white box that behave like the black box, you can explain the interpretable model when you have some questions about the black box. And this is still an ongoing work. It's not trivial that it's sometimes the best thing to do, because in this simple example, you could see that on the x-axis, you have the number of nodes of decision tree, so a dimension, a proxy of the complexity, if you want. And the y-axis is a measure of how well is going the model.
Sure.
And yes, you can get a better decision tree, better the surrogate trees when you train on this input-output relationship, for example, of a black box, but at the price of increased complexity. So there is always this tension between complexity and accuracy. Did you have a question? Sorry.
No. Go on. No problem. I think it's quite clear.
Okay. This is the other aspect. You can go post hoc for explaining a black box. So we have the black box. Let's just explain the black box. And this is what we said before. Now, you can have there is this class of methods that is called feature attribution techniques. is basically answering the question, what was the impact that the features had on the prediction? How important was a feature in the prediction? And here you can see, I wanted to expose you to this very interesting behavior that was discovered. So there is this task of distinguishing images of husky versus wolves, and this was a sample of the data set. And in principle, it's a very complicated task for humans too, because huskies are similar to wolves. Yeah, they are different, but they share a lot of features. For some reason, the neural network were able to discriminate 100% of the time, or almost 100% of the time, like super high accuracies. Why was it the case? Then you can apply this interpretability and see why is this the case. So look at this picture. Of all the picture that there is, this is predicted as a wolf, but the golden truth is that he's an husky. So we can ask, why do you think this was a wolf? And the prediction and the explanation is, look, I think this was a wolf because, well, these pixels were the most relevant into guiding me to understand that it is a wolf. What is this? This is the snow. You can see from the original dataset that there was an implicit bias, so that all the huskies were depicted into a more a non-snowy environment, while the wolves almost always in the pictures were in a snowy environment. So this is what I said to you before. In a sense, this neural network is getting the concept that wolf is a snow, and husky is non-snow. So even if you, in this case, if you said, well, the explanation must lie on the wolf or on the husky, you are implicitly inputting some bias human bias in the evaluation of how you think the model behaves. But the model might behave in weird way that we don't expect, that still answer the question or solve the task. But of course, in another application, the task at least of this data set, but if you want to develop a business on this image detector of husky versus wolves, you will be, your system won't work properly. So this is interesting, and this is also highlighting how the nuances of how do you evaluate these explainable systems. You can have a similar thing that I showed you here for tabular data. It's called Shapley Values. You might have heard of it or not, but basically it's, as before, it's answering the question, what was the impact that the feature had on moving the model away from its baseline? There is a very formal mathematical way. I will try to get just the idea without having to go too much into the details, but it's taken from game theory. And the fact is this, suppose what is a game in game theory? It's just, you have a collection of players, which means some entities that play a game. Competitors. Well, no, it's collaborative in this case, for example. So they form a coalition, and the coalition has a certain value. So for example, I don't know, a game that is easy, like we play basket, and we are in 5, and you score some amount of points. The game, in this sense, is not really the basket game, but it's the fact that you 5 scored 15 points. Okay, another team might score another set of points. The question of Shapley values that I try to answer is, okay, we scored 15 points. What is the merit of each person? Okay, because some people played more, some people played less, and the idea is
the wolf, no?
This. Yes, the idea is to calculate this. Is what is my, for example, in this, if I play in this team, what is my added contribution to this team? Which means, from a practical level, with me, we scored 15 goals. With if we take an average person from the street, or from basket players, and this is where you take it to change the definition, but let's say from the street, maybe the same team would have scored only. So my average contribution is 15, where I'm present in the team, minus 10 when another person, a generic person, is in the team. So there is this 5. You can do this average, this marginal contribution thing for all the possible coalitions that might exist. So you can do the same for you, and also you, instead of removing 1 person, you remove 2 person, you remove 3 person, and so forth, replacing them with average person from the street. There is a nice formula. So this is the marginal contribution idea. So what is the value of the game of the coalition with the player I, for example, with the player me, minus the coalition without me. And in the machine learning, it becomes what is the value of the data point with this specific feature I, minus the average value of the data points without knowing what is the value of this player.
Sure.
I know this might be complicated to follow, and it is, but it's a mathematical sound way of computing this attribution in such a way that also they sum up to the difference, and that if a player didn't contribute at all to a game, he gets 0. He or she gets 0.
Interesting.
What?
Interesting. I never went through this definition. Thank you.
Was it clear with this explanation?
Sure. Maybe if other people have questions, I think that they can comment on the. They put some comments. No.
Don't forget to like and subscribe.
Yeah. And so, then you can answer.
I personally use this concept of Shapley values as an heuristic for complexity. So I might ask you, Chip, do you believe here are 2 explanations coming from the same dataset, same model, but 2 different data points? Is explanation A simpler than explanation B, or vice versa? I would suggest that explanation B, in virtue of being smaller, it's at least more digestible. Like, I need to read less impact scores before getting whatever idea I have of how the model behaves.
Absolutely.
So you can extend this idea to have this definition of sharp length, which is if you were to compress lossy this idea and getting only the 80% or the 90% or 95% of the explanation mass, which is the absolute value of the Shapley values, how long is the explanation? And this is, in a sense, you can consider it as a proxy for understanding as a measure of understanding how complicated a model is. And you can run this for each explanation in a data set, and you can have a number that tells you how much it's, in a sense, complicated, how much is an estimate of the cognitive load on a user if he or she were to go through all the explanation on the data set. And it's nice in the sense that it's proportional to some well-established metrics of complexities. Like for decision trees, you can see the number of rules or the number of leaves in a decision tree, and they're proportional, which is nice. And the nice thing is that why is it important to have such a metric? Because now you can compare models that are in principle very different from each other. Because you compute usually the complexity of a decision tree based on the number of leaves or on the number of decision points that you have. While on linear models, you usually compute what is how many non-zero coefficients do you have. And instead, if you go into the Shapley values and you compute the the compression, of these Shapley values, you can have an homogeneous metric in order to uniformly compare even models that are very different to each other.
Got the point.
So as I showed you, there are also these feature attributions for text. But this I'm going just to show you very quickly. You can, in principle, do the same thing as the Husky Wolf. So why do you think this is like this? And for this generating model, like, you might have heard of large language model, ChatGPT, GPT-3, GPT-4, and so forth.
I know that sometime in this presentation that name would appear.
It would have come up, yeah, of course, because I find it beautiful, if you ask me, as a technology.
Sure.
And how is it working underneath? It's just predicting the next token, no? So my job is to make a new prediction. And basically, what you can do with feature attributions, in this case, you can at each next token, you can ask, okay, what token was important for highlighting this as the next token? And this is, to be fair, an ongoing work. We still don't have many results, because you can make this nice temperature plots, in a sense, but it's not necessarily trivial to then interpret them. And also, there are many different competing methods for computing such pictures, such results, such explanations. And the question is, how can you assess the faithfulness of these? Like, which method should I choose? Which method can I trust if I have to do further analysis of this data? And so I focus for now on the easier question of how can we assess the faithfulness of these feature attribution methods. And I will go very quickly with this. This is work done in collaboration with two colleagues, by the way, Anaria Duarte and Michele Capagna. The idea is pretty simple. You compose a new sentence like this, which is based on sentence 1 and sentence 2.
Sure.
For example, sentence 1 is a positive sentiment, while sentence 2 has a negative sentiment. And you ask the model and the tool, explain me why this sentence as a whole is positive. By construction, I would expect that if the model works correctly and explanation tool works correctly, most of the positive attribution should lie here with respect to here.
Sorry, in this case,
so we can have a measure.
Sorry,
yeah.
The notion of positiveness is like a positive feeling, sorry, or do you have a precise?
Yeah, there are data sets of sentiment,
okay.
Like very easily, like this movie was very nice.
I got the point.
Okay,
yeah, sure.
As a positive sentiment.
Perfect.
Okay. And you see, this is an example. These are two tools that exist. This is the sentence, I love running, and this is the attribution. This method tell us that I love running contribute positively to a score of a positive sentence, of
sure.
a positive, sentiment. I hate to write the introductions. Here the word hate is really dragging down the score. A delicious cup of tea is positive. What a horrible movie, and here is negative. And basically, based on this constructed ground truth, by measuring how much is it lying correctly with respect to how much is it lying incorrectly, you can get some measures of faithfulness. And yes, this method is sound because it works on a randomized model. It's 50%, and you can evaluate many methods and have an idea of how faithful they are.
Sure.
So, just for wrapping up the conversation, would you ever trust an algorithm in that very important scenario when you have to go to a bank loan or to the doctor or to law? And my answer would be yes, but only if it can explain itself better than I just did in this presentation. Never settle for a random output. And I think this was my presentation. By the way, I would like also to mention that I'm thankful for the NL4X AI project that is providing me with support for going on with my PhD and funding my research.
So, Ettore, thank you very much for this presentation. I think that you have been quite, at least for me, quite clear. And I would say I don't have particular question because I would have too many questions because I think the topic is so wide. Future perspective. Now, what do you think is so you mentioned ChatGPT.
Yeah.
What is the application of explainable AI on the development on ChatGPT? I know that it's not probably a well-posed question, but it was more about future perspective on this.
No. Let's try to tackle the future perspective. So first of all, the whole field of XAI has to understand really how to evaluate the explanations.
Sure.
Well, better to clarify what the explanation is, but you can only do it by applying in the field, I believe.
Sure.
Because different tasks have different requirements or even different definitions. Also because you are trying to answer to different group of people. And for example, I know that OpenAI stresses a lot the importance of explainability.
Sure.
Because by having a model that is explaining itself, or that you can explain what is going on, you
Sure.
can try to explain what is going on. You have a holder grip on the problem of alignment, which is are the models aligned with what are our values, with what are our considerations? Why are you doing this instead of that? Also, there is, of course, on the topic about trustworthiness and trust in general. There is one problem, for example, that I think there are some science fiction stories about it, that basically you start with, you pose an objective, and the objective is sensible and even innocuous in a sense, but the model find a perverse way of optimizing it.
I've seen this, like playing video game, automatic video game players. I remember I've seen a video on YouTube that was like a way of I think playing Mario Kart. I think was, but in a really weird manner that a human player would have never had done.
Yes, exactly. Or I don't remember the story, unfortunately, but basically the program is tasked to optimize some quantity, which is to duplicate information, and the optimization process goes out of control, and the model starts to destroy every information that humans have ever produced. This is, of course, a catastrophic case. I personally like the fact that with explainability, we can, like these artificial intelligence models, which now I feel more comfortable in calling artificial intelligent models, can really maybe, quote, see things that we don't see. Also in virtue of the fact that we cannot see 1,000 numbers at the same time,
exactly.
Or that we cannot, we have a limited amount of books that we can even read in our lifetime. And so we can start building a bridge between these different ways of understanding, this different way and basically they can be a tool. So right up to now, we've been programmers that we tell the computer what to do, and the computer does it and return a result. And now we let the computer learn what to do by examples.
Sure.
And the explainability, what could tell us is new ways of understanding how this process behaves. For example, also in climate, imagine that you build a climate model of how the climate is evolving, the weather is evolving. And if you have a black box, you can only say, oh, temperature is increasing of 2.2 degrees Celsius, if it was black box, for example. But if it is white box or interpretable, you can use some explainability. In principle, you could say that, oh, look, this current is very important into the behavior of this other process.
Sure.
And this can also inform the scientist to say, okay, the models say that this current is very important. Let's go and sample more data from that current. Let's see if that's really true.
Sure.
Can really also guide the experiments in a sense. And I'm really fascinated between this interaction that there could be.
I definitely agree with your answer. So, okay, I think we have reached our time, and so again, Ettore, thank you very much for for accepting my invitation. I wish to have another discussion, maybe more in detail next time, or to maybe go more in deep on some part that we don't have no time to treat today. And so again, thank you very much, and yeah, see you soon.
Invitation.
Bye.
Bye bye.